go. Yep.
Okay, and I should be in full screen now, correct?
Yep, you are.
All right, well, thank you. I think we can do fine here in terms of the time allotment. I have a very few set of slides here. This topic was born out of noticing that in the actual implementation of products related to networking or transport, a lot of the timing sync solutions are implemented in various and assorted ways with various assorted inputs and outputs on products, and it's not potentially OCP defining a modular timing synchronization element that could help standardize some of that and make it more common across various products that OCP customers would be consuming. I am currently the CTO of EdgeCore Networks. I am really not doing this presentation on behalf of EdgeCore Networks. I'm rather doing this on behalf of OCP as a potential area of contribution as a specification. So the kind of three things I'm going to go over are just a summary of typical Sync-E PTP topologies and implementing the functionality. Looking at the modular timing sync design space, and then looking at the timing sync ports, the menagerie of connectors that are various and assorted products.
Okay, guys, is it me or is the audio not working?
I think we lost him. No, it's really bad. Yeah.
Okay, Lauren, I don't know if you can hear. I don't know if you can hear us, but it sounds like you're underwater, and we're catching every maybe fifth word.
Let me see if I can fix that.
Yeah, I'm not sure if it's your connection, Lauren.
So is this better?
Yes.
Actually, my PC has weird problems. So I plugged
in my headphones. That is much better, yeah.
Yeah. Sometimes it works, sometimes it doesn't. So I apologize for that. So I was saying that I'm just going to run through kind of the common ways that timing sync is implemented in systems. And then we'll talk about kind of the design space for a modular approach to implementing hardware related stuff related to timing sync. That includes timing sync. Two things that have to come together. One is some source of frequency or clocks for the node, and then a way to run the PTP algorithms. And so typically the frequency is done off a Sync-E, which is done off recovered clocks from in-band Ethernet traffic on a particular port on a node. You can see that highlighted in red here, where the port receives traffic, clocks are recovered. You run that through some circuitries that clean up and generate a very stable clock. Then you feed that back into the switch ASIC as the reference for the transmit clocks, thereby synchronizing both the recovered clocks to the transmit clocks. Obviously,
okay, Brian, sorry, Lauren, we've lost you again.
Yeah.
Lauren, I'm sorry, your audio is just fading and coming in. Would it be better if I can maybe flip the slides for you and you can just use your audio?
I think the slides is fine. I think it's just the audio.
Yeah.
I don't know what to do about that.
Well, it seems to be better now.
Okay,
Mike and others, can you guys hear? Maybe it's just me.
No, he's been dropping out. He's been an out, but
Okay, go for it.
choppy.
We'll see what we can
I'll
do.
stop and see what happens here then. And the second piece of this is where you run the PTP algorithms. And the slide here shows running the PTP algorithms embedded in the switch ASIC. So some providers of switching ASICs have microprocessors inside where they can run the PTP stack. A second way of running the effort is you actually run the PTP stack on the host processor. And again, here, the PTP packets would come in through and then get redirected to the host processor via Ethernet or PCI Express connections. And the PTP stack would actually run on the host. And there are several companies that build stacks that can run on host, or a lot of software companies that are in the networking space actually create their own PTP software that they want to run on the host CPU. The third option here is where there's an additional add-in processor separate from the switch and the ASIC, and the host processor, host CPU. Again, the PTP packets come into the switch and get redirected to that independent processor via Ethernet link. And you run the PTP protocols on that microprocessor. You'll see here, I've outlined kind of a blue area in our area of the diagram in the dotted blue line. And this is the area where there's potential for modularization and standardization. This would serve both functions of providing the required circuitry to create syncy clock and to run the PTP protocols. And the idea is either this is a standardized module, it could be optional. So you could run a system where you weren't supporting Synchy and 1588v2 and just run the clocks in a free form, or in this module will take over the clocking functionality. Kind of the proposal here is two definitions of a modular timing sync function. One would be a full definition, basically an add-in card, perhaps externally accessible, and would include defining the connector, potentially the front panel in terms of the ports required to access and monitor timing sync signals. And then you can see the various sort of functionalities that you might want to put on a timing sync module here in terms of an ARM processor, DPLL, a GNSS or GPS receiver, the high performance OCXO crystal, and other components that would make this subassembly work. In the diagram for some megahertz input or